Okay, this one was really hard to do just because of the sheer volume of science contained within it. Now, something I generally love is finding books that are, the science of. In truth, I probably want to write those books. But there's no point in a The Science of the Martian book. Andy Weir already kind of wrote a textbook all about how to survive on Mars. So just read the novel because it's all there in excruciating detail. Now, in the nearly 10 years since the movie came out, there have been many articles and YouTube videos that all cover the core topics, and I didn't want to just kind of repeat that. I wanted originally to do one long video covering all of the science, but I realized that that video was going to be about 3 hours long, much longer than the movie itself. Truthfully, I reckon I could actually give an entire university lecture series on the science of this story. So what I've decided is that for right now, I really just want to talk about space travel. So I'm going to leave a lot of the other stuff out for this video. And I've been dying to talk about the Rich Purnell Maneouver for a long time now. So let's deep dive into the wonderful world of space travel according to The Martian.
In your face, Neil Armstrong.
We're going to kick off talking a little bit about NASA and the movie itself, because this movie is, in my opinion, a billion-pound advertisement for NASA. And I don't mean that as a criticism. What I mean is that the detail and the execution is so good that it serves NASA well to be heavily supportive and accommodating to Ridley Scott and the rest of the team, of course. Contrast this with a movie like Moonfall. If you're NASA, you kind of want to distance yourself from that, but with The Martian, you throw those doors open wide, and by hell they did. Some of the science consultants on this movie were the likes of James L. Green, the director of Planetary Science Division. We have Dave Lavery, who's the program executive for solar system exploration for NASA. The on-site technical advisor for the movie was Rudy Schmidt, a scientist from the European Space Agency. They then created subgroups of experts and specialists that were on hand to answer any and all questions put forward by the production. Arthur Max, the production designer, was invited on a tour of the Johnson Space Center and was allowed to take as many photos as he wanted. Drew Goddard, who was the screenwriter, was taken on a tour of JPL. NASA also arranged for the costume designer Janty Yates to meet with a curator of the Smithsonian Institute that houses a collection of historical spacesuits. Jessica Chastain shadowed Tracy Caldwell Dyson, who's an astronaut who'd previously spent time on the ISS. They also sent images of Mars, of NASA control rooms, and they included images of what computer screens would have on them, and all my nerds know what's on the computer screens is important. The attention and accuracy is astounding in this movie, and it really shows you what you can achieve if you offer NASA a free ad for space exploration. So let's go on a mission to Mars. The Aries program is Andy Weir's Martian version of the Apollo space program. So the Aries program is funded for 5 manned missions to Mars. 2 of those missions have already been successfully carried out, and Aries 3 is underway with the team due to be on Martian soil for 31 sols. Now, just if you're curious, a Martian sol is 24 hours and 39 minutes, so 31 sols is almost 32 Earth days. Now, why is a mission to Mars such a goal for humanity? Well, the simple answer is that it's possibly one of the only other places where life may have existed in the solar system. So scientists believe that studies of Mars can tell us more about Earth, about our past as well as our future. Now, there are many other places in the solar system where life could exist, so places like the moons of Jupiter and Saturn, such as Europa and Enceladus. These moons could have liquid water under the surface, which could harbor microbial life. And this would be really important discovery, because if we found life out there, then it suggests that life is actually far more common in the universe than we thought. But given how far away they are, human trips to the moons of our gas giants are not likely until we achieve a trip to our nearest neighbor first. Getting there, though, is the challenge. You see, it's not just about the distance. There's cost and safety to consider. We can easily look forward to what it should be, and Andy Weir's portrayal is pretty close to reality. but there's a lot of scientific advancements that need to be made before we can actually achieve it as a reality. So let's talk about something that I love talking about: astronauts.
Copy.
How long do you think astronauts would train for a mission to Mars? Now, during the shuttle program, astronauts train for 8 to 10 years. First, you have to get into the program. Now, to get into the astronaut program, you need a master's degree in a STEM field. You need 3 years of professional experience in that field, and you need to pass the long duration flight physical. Also, the pilots will need to have 1,000 pilot in command hours, with 850 of those at least being in a high performance jet aircraft. So, in the movie, who qualified? Well, we got Commander Lewis, former US Marine, geologist and disco fan. We have Pilot Major Rick Martinez, former US Air Force. We've got Beth Johansson, who is the systems operator. We've got Dr. Chris Beck, the flight surgeon and EVA specialist. Dr. Alex Vogel, who is the flight navigator and chemist. And we have Dr. Mark Watney, or botanist and mechanical engineer. Now, once you qualify for the astronaut program, you're technically an astronaut. You just don't automatically have a mission. You see, space agencies like NASA typically have more astronauts in their pool than they have available mission opportunities. And once you're on active duty as an astronaut, getting assigned a mission, it's highly competitive and it requires rigorous training. Now, a lot of astronauts in their time will serve as technical experts. They'll work in mission control or research and development. They'll train new recruits, and they will retire from active duty before ever receiving a mission assignment. Now, one of the reasons for this is because missions can take decades to plan. And then once they are planned, the astronaut selection can happen maybe a few years before the launch date. Candidates will then undergo a rigorous selection process, including medical examinations, psychological assessments, interviews, evaluations of their technical capabilities. It really depends on what the mission needs. So the mission planners are trying to identify individuals who are best suited for both the mission specifics, the challenges of long duration spaceflight, and people who will work well together. Teamwork is vital for a space mission. Now, once astronauts are selected for the mission based on their different specialities and the tasks that they will then have on the mission, they then undergo mission-specific training, which could take a few years. Now, as well as all the training you would expect in terms of the spacecraft, its systems, spaceflight operations, spacewalks, emergency procedures, research, protocols, there's a lot. There's also physical conditioning, survival skills, and psychological preparation. Now, what I've said so far is just a mediocre slice of the skill set of an astronaut. The point is that, in my opinion, they are the most highly trained humans on our planet, technically, physically, and mentally. Astronauts are prepared. And this is one of the reasons that this movie is so beautifully done. It's possibly the best character representation of astronauts on screen. Now, Andy Weir said originally that he wanted to write a science story, so he deliberately wrote Watney as optimistic and a resourceful character, someone who would just work the problem. And psychologists have actually determined that a sense of humor would be vital to surviving the extremes of this kind of a mission. And apparently, it'll win you a Golden Globe for Best Picture for a musical or comedy. I am still mad about that.
Surprise.
Now, to get to Mars, you're gonna need a spaceship, and the Hermes is one of my favorite sci-fi spacecraft. It's kind of like a little bit Discovery 1 meets the ISS. I would go into space on this ship, like I would say yes to the dress. Now, the ship itself was built in orbit, so it uses ion propulsion technology, which allows it to accelerate continuously throughout the journey. Research into ion propulsion has actually been going on since the 50s. This is because ion engines have a high specific impulse, meaning that you need a lot less propellant to gain thrust. Now, there are a number of satellites in orbit that use ion thrusters, and as far back as 1998, NASA's Deep Space One mission served as a proof of concept for ion propulsion in long flight missions. One of the most well-known spacecraft to use ion engines is NASA's Dawn spacecraft, which was launched in 2007 to study the asteroid Vesta and the dwarf planet Ceres in the asteroid belt. Dawn is equipped with 3 ion thrusters so that it could maneuver and change its trajectory during its journey between different celestial bodies. Its mission ended in 2018 and it remains in a stable orbit around Ceres. So what is an ion engine? Well, an ion engine uses the principle of electric propulsion to generate thrust using electrically charged particles. The first stage is to ionize a propellant gas like xenon, and there's many ways you can do this, but the typical method is to use an electron gun to knock electrons off the xenon atoms, leaving behind positively charged ions. Now, a system of electrodes that are charged to high voltages then create an electric field in the chamber that attracts the ions, causing them to be accelerated. The accelerated ions exit the chamber through an exhaust nozzle at the back of the engine, creating a stream of exhaust that creates thrust in the opposite direction. A traditional chemical rocket engine will produce short bursts of high thrust. An ion engine can operate continuously, producing low thrust but high efficiency, allowing for gradual acceleration over long distances. An ion engine is the most logical spaceship engine for long-duration missions to deep space. When it comes to the visual design of the Hermes, like I said, Discovery 1 meets ISS. We've got these large solar panels that capture sunlight to generate the electric power needed for all of the ship's systems. And then we've got these modules that have zero-G that contain some system operations, flight deck, docking ports, and so on. And then there's the centrifuge, which acts as the habitat module for the crew, a rotating torus that generates artificial gravity. This is absolutely the most likely way you could generate artificial gravity on a ship. The centrifuge rotates at a constant speed, measured in revolutions per minute. This rotation generates a centrifugal force that pushes outwards on the objects and the people inside of the module, creating a sensation of gravity perpendicular to the rotation. They would basically feel like they are being pressed against the floor of the centrifuge. Now, being weightless for long periods of time can lead to muscle atrophy. So if we ever have any hope of taking long duration voyages in space, we have to be able to counter these effects on the human body. If you've seen The Expanse, the belters are a great example of how our physiology could be affected by living in low gravity. Now, the rotation of the centrifuge really doesn't need to be that much to generate 1G. I was honestly surprised. It comes out at about 7-ish revolutions per minute, which is slow enough that there likely wouldn't be many physical effects other than the sensation of gravity. The crew would, of course, have to train for it, but once adapted, there shouldn't really be any reason that they wouldn't be perfectly fine. Now, personally, I thought that they'd get motion sickness, but apparently we're pretty adaptable as humans. I still maintain that I would get motion sickness. Like, a highly trained astronaut probably wouldn't, but I absolutely would. So, if we have a large ship equipped with everything an astronaut needs for a long duration flight, how long is that flight? Or how far? What is our path through space to Mars? All of the planets in the solar system are all moving, always. Now, we can approximate really well the orbits of the planets, but no orbit is perfectly circular. So there are times when planets are closer to us, and there are times when they are further away. When Mars and Earth are both at their furthest points from the Sun, known as the aphelion, they would both be around 400 million kilometers apart. When just Earth is at aphelion, furthest point from the Sun, and Mars is at perihelion, its closest point to the Sun, then the Earth and Mars would be the closest they possibly can be, about 54.6 million kilometers. Now, in our entire recorded history, the orbits have never lined up like that as yet. The closest we've ever come was in 2003 when we were 56 million kilometers apart. Now, this won't happen again until about 2237. As I'm recording this, Mars is about 140 million kilometers away. Now, because of the duration of our orbits around the Sun, mission launches have to be planned so that they occur only when planets are on a close approach. For Mars, this happens around every 26 months, and this is what's called the Hohmann transfer window. This isn't just for Mars, by the way. This is for all objects in our solar system. They all have specific Hohmann transfer windows that can be open for a few weeks or maybe a few months. And this is why some launches get scrapped and pushed by what seems like a long time, but it's really just that they have to wait for the next launch window, the next lining up of the orbits. And this is also why there's such a huge push to get the probe ready. You see, they have to launch it before that window closes. If they don't send it now, it'll be 2 more years before they could send it, at which point Watney will already be dead. Now, they still have a little bit of time because the window will stay open for a couple of months. Unfortunately, one of the HAB airlocks buckles under the pressure from overuse, because it's only designed to last 31 days, not months to years. And this destroys Watney's crops. The result is that they have to push up the launch time of the probe, massively cutting into the preparation time and ultimately making the fatal decision to skip the safety checks. Now, launches are not guaranteed. Any number of things can go wrong, and while the movie makes it clear that skipping the safety checks led to the failure, this doesn't exactly mean that if they had done the checks that it would have succeeded. Even the most thought out launches that have years to prepare, where systems are like double, triple, quadruple checked, they can still fail. All it takes is one unexpected event. So, what happened to the probe?
We are getting a very large precession.
Are we good?
Rockets and payloads are very specifically designed to suit each other, to ensure that all of the forces and everything are in balance. Now, the food that they were sending to Watney were protein cubes that are a combination of solid particles and vegetable oil. But the rocket that they were using to send the payload was designed to accelerate faster than originally planned. And the additional forces and pressure caused the protein packets to liquefy. Now, once the food was liquid, it could move around more and caused a force imbalance in the payload. During one of the stage separations, the impact of the liquefied payload breaks one of the 5 structural components holding the payload. Originally, the other 4 would continue to hold it together, and this wouldn't have been an issue. However, one of the struts was faulty, and since they skipped the safety checks, they never found it, and this meant that 2 struts ultimately failed, and 3 were not enough to hold the payload. So once the struts failed, the payload was loose inside the fairing. The fairing is the nose cone that protects the payload against the pressure and the heat of moving through the atmosphere. With the payload loose, the rocket was then thrown off balance, and under all the unexpected forces, it broke apart. With this failure and the offer of the Tiansheng probe, what would you do next? You see, all you can really do is prepare another payload and hope that this one succeeds. But the failure rate of a probe launch is anywhere between 5 and 30%, so it's a big gamble no matter what. Now, if the probe gets to Watney, he will have enough food to last until the Aries 4 mission is scheduled to arrive 4 years later. But that doesn't necessarily mean that he will survive. The current mission's materials are only intended to last for a 31-day mission on the surface. The longer he's there, the more risk there is to the HAB failing, problems with the available spacesuits, systems failures, any number of things could go wrong. It would be better if they could get him home.
I'm sorry, what's your name again?
Teddy. I'm the director of NASA.
Cool, Teddy.
Michael Minovich was a trajectory analyst at JPL in the 60s, and he came up with the idea of gravity-propelled interplanetary space travel. But nobody believed him at first. In 1961, he submitted a 47-page technical paper that was dismissed by the head of JPL Trajectory Group. You see, he thought it was impossible. He also didn't believe that a graduate student could come up with a working idea, especially one with no background in reaction propulsion. Minovich was a mathematician. But once he walked the senior management through his idea using a chalkboard, they realized that it was possible. And in 1973, Pioneer 10 was the first mission to use a gravity assist to increase its velocity as it passed by Jupiter. Now, whether it was intentional or not, the whole Project Elrond scene with Rich Purnell explaining the planned trajectory to Teddy feels like a nod to Michael Minovich. I feel like it had to be intentional, right? I'd love to know. Now, back when our solar system formed, the sun took 99.8% of the nebular mass. The remaining 0.2% is what makes up all of the objects of the protoplanetary disk. Now, when this all happened, the intense ejections that created it transferred angular momentum from the sun to the objects that make up the protoplanetary disk. Today, the planets still retain most of the solar system's angular momentum, and this momentum can be tapped to accelerate spacecraft on gravity-assist trajectories. You see, what we want is to use a planet's gravity to change our direction and gain some speed. Now, the Hermes will approach the Earth at an angle, and as they get closer, they begin to feel some of the gravitational force from the planet pulling them towards it, increasing their speed. Now, here's the key part. You see, all objects exert a gravitational pull on each other, no matter how small. This means that some of the angular momentum from the Earth is transferred to the Hermes, giving them just enough velocity to escape the gravitational field of the planet and skim past it, but with a new trajectory and having gained some velocity and angular momentum. Now, later on, when they fly by Mars to pick up Watney, they again perform a gravitational slingshot, getting a bit more velocity for their trip home. Now, one of my favorite things is nerds getting super nerdy about this stuff, so it brought me one of the greatest pleasures in my life when Laura Burke of the Mission Architecture and Analysis branch of the NASA Glenn Research Center wrote an examination of the Martian trajectory. Burke concludes the analysis with confirmation that all the trajectories proposed in the book are consistent with both the laws of physics as well as the expected performance of an ion propulsion engine of this kind. I love nerds. I'll link the notes, or I'll put a link to this paper in the description so you can find it and read it. It's really cool. So the gravity assist will work. All the orbits and trajectories line up so that the Hermes can actually get back to Mars. The problem is that they can't go into orbit around the planet.
Go faster than any man in the history of space travel.
Like that's a good thing. Like it'll distract me from how insane their plan is.
The Mars Ascent Vehicle, the MAV, for the next Aries mission is waiting at the Schiaparelli crater. Schiaparelli crater, that place. The problem is that the MAV, as it is, won't be able to reach the height that the Hermes, what has happened to me? The MAV won't be able to reach the height of the Hermes, oh my God. The MAV won't be able to reach the height that the Hermes will be at. Well, okay, good, we've got that. The thing is, for an object to get into orbit, they have to travel at a specific velocity to escape the gravitational pull of the planet. So you need a certain amount of fuel to be able to do that, to be able to push the mass up into orbit. The rocket equation then, or the Tsiolkovsky rocket equation, because it was first published in 1903 by Konstantin Tsiolkovsky. I'm sorry, there's just 1903. It just, oh my God. Anyway, this equation shows the relationship of the fuel and the mass to the velocity. So when we look at the equation, delta V is the change in velocity from 0 to the speed that this much fuel can push this much mass. Let's have a look at this without using numbers because we don't know what the real heights are. What we do know is that to reach the Hermes, Watney needs to have enough fuel to push the mass that he has to the height that he needs to get to. Well, we know it's not going to be enough because the MAV is designed to go to a low orbit. The Hermes is supposed to be in orbit around the planet when the MAV is being used. So we know that it has a set amount of fuel, so it can only reach a set height with the mass that it has. The only thing that we can change is the mass. They gotta strip it. They gotta send him into space under a tarp. Now, this might seem totally crazy that he could shoot up into space under a tarp, but remember, Mars doesn't have an atmosphere like ours. Our atmosphere is very heavy. It's very thick. There's a lot to push through, but Mars, it's half the size of Earth and it has an atmospheric volume of less than 1% of ours. Watney doesn't actually have to get too high for the atmosphere to be irrelevant. The tarp is really only there to provide some sort of aerodynamic purposes, since they're, taking off the front of the spaceship. But getting up into orbit is only one part of the puzzle, because he also has to velocity match the Hermes.
Velocity 850, altitude 1843. He's well below target altitude.
So velocity matching is fine if you're in the same orbit, if you're in the same distance from the surface. The orbital velocity equation shows us that it only depends on the mass of the planet and the height of the orbit, not the size of the object. So all satellites that are in the same orbit travel at the same velocity. So if Watney reaches the height that the Hermes is at, he has the same velocity. This means that once the intercept angles are set correctly, then there's going to be very little difference between the speed that the MAV is traveling at and that the Hermes is traveling at. Let's think of it this way. Think of two cars on a motorway. So if you're both going at the same speed and you look at someone in the car next to you, they look almost stationary compared to you, but you're both moving compared to other objects around you. Now, I'm not saying it would be easy, but you could potentially jump from one car to the other. Now, the problem for Watney is that on the way up, the tarp comes loose, so he gets shifted off course and reaches a lower orbital path. This creates a much larger distance between them, but this distance also means that there is now a very large difference in their relative velocities. The closer you are to the surface, the faster your orbital velocity will be. So think about it like this. The ISS is in low orbit and that orbits the Earth every 90 minutes. A geostationary satellite is in high orbit and that orbits every 24 hours. In our car analogy, now it's like trying to jump from a car in the fast lane onto a car in the slow lane. Watney can't get any higher. He is out of fuel. The Hermes doesn't have enough fuel to alter its path, so there's only one way that it can get closer to Watney. Blow up the airlock. Now, how realistic this is, I'm really not sure, but I would buy it. The rapid release of air out of the airlock acts as a thrust to push the Hermes closer to Watney, conserving the fuel that they need to get home. I'm assuming that the distance between them isn't so much that it affects their gravitational assist trajectory and that they're still able to skim around it. Unfortunately, it's still not enough. The velocity difference is okay, but the distance is still off. Watney can't get closer to Commander Lewis and she can't get any closer to him. And he's just like spinning around in a beat up tin can anyway. So there's only one thing left to do to close the gap. He's gotta go Iron Man. Now, while using pressurized gas to get thrust in space is entirely possible, you'd be better off using a fire extinguisher to get there. You see, a spacesuit just doesn't have enough pressure to generate thrust. It would actually be more like, letting out a balloon very slowly. At the end of the day, we can let some things go for the sake of storytelling. I love this whole sequence. From the moment Watney hears Commander Lewis's voice all the way through, it's such a great payoff. I still get emotional every time I watch it, to be honest. Now, I know there's a lot more that we could cover with this movie, but to be honest, it's all in the book. So if you just read the novel, you get such detail on the science of all of the cool stuff happening on Mars. But if you do have any questions, you can leave them in the comments and I'll try to respond as best I can. But that's it for me and space travel according to The Martian. I hope you enjoyed it. Thank you for watching. I'm Abby, I'm a physicist. I'm working on my PhD at the University of Oxford and I nerd out on sci-fi most of the rest of the time. So if you like that, follow along, and if you have any topics that you'd love me to cover, then do let me know. Toodles! I got him! I got him!
Way to go, Iron Man.